Let us recap the capacitor again. So once again, whenever we talk about a capacitor, the first thing that should come to your mind should be I is equal to C dV by dt. If you remember this thing, obviously the other things will sooner or later come to your mind, or you can even derive them if they are not there, or you can always look them up. And similarly, when this thing comes to your mind, the other thing is that the voltage of the capacitor is equal to 1 over C integral of I dt. And one of the expression is Q is equal to the charge on the capacitor is equal to CV. The current state of voltage can tell you how much charge it holds. And the last expression in this regard is that the energy a capacitor stores is equal to half CV square. So knowing these expressions, we know everything about the capacitor from a circuit analysis point of view. In circuit analysis, we are not usually concerned about the construction of the capacitor, what goes on inside the capacitor, but what we are really interested in is the terminal behavior. Exactly. So if we recap the capacitor, let me write the recap things here just for your reference, and then we are going to look at some currents and voltages and see if we know one, how can we find the other one. So one very important thing about these expressions is by looking at this expression, we can see if V is constant, dV by dt is going to be 0, which tells that I would be 0. So when a capacitor in a DC circuit gets charged, the voltage no longer changes, it stays constant, and the capacitor behaves as an open circuit. This is the other thing that we know, that capacitor behaves as an open circuit for DC sources. Let us say it in this way. Although we are going to add the word steady state later on, but for now let us just accept this. Then what we know this, just looking at this expression again, we know that we cannot change V instantaneously. Or abruptly, or suddenly, whatever word you use to signify that the change happens in zero time. We cannot change V instantaneously is not possible. Why? Because a suddenly changing V requires infinite current, because I needed to be of infinite value, which is not possible. So somebody says there is a capacitor. Currently, it has a voltage of 5 volts across it. Let us change this voltage to 10 volt within no time. So it's not possible. That's the point. So graphically, this can be more easily understood that there is a capacitor at some interval t1. It has a value of 5 volts. And it suddenly we want to make it 10 volt, then this is not possible, because when the voltage was 5 volts, there was zero current in the circuit. After becoming 10 volt, the 10 volts voltage will stay constant across the capacitor, so there will be zero current. But this change in voltage, as we can see, the change in voltage is related to change in charge, because C does not change for a particular capacitor. So it means we need infinite current to flow in the capacitor, and this is not possible. And the fourth thing that we should be mindful about is that a capacitor never dissipates energy. This is very important. A capacitor, you can only get energy out of a capacitor if there is some energy stored in it. So you store first and then the capacitor releases energy. Before more energy is needed, you must store more energy in it. So it does not dissipate energy. So obviously this is when we talk about the ideal capacitor. In a practical capacitor, obviously there are the dielectric is not a perfect insulator. There are some leakage currents there and it dissipates energy, but the ideal capacitors that we study do not dissipate energy. So with this recap of a capacitor, let us come to a question. Say somebody tells you there is a capacitor. Let us keep it simple first. Of 1 farad, a humongous, huge capacitor, but it does not worry us to have such a big capacitor here in this question. And let us say the voltage across it is shown through this graph. So we can say the voltage is initially 0. It then changes gradually, so not instantaneously, to some voltage, say 10 volts. So we are not going to write volts here because it's there in the access description. So after 1 second has elapsed, after our interest in the capacitor has started, its voltage started rising, and then after another second has passed, its voltage reaches 10 volt, and then it stays there. So our job is to find the current and plot it. So both are required. So we should be able to do this mathematically as well as intuitively, and we should be able to plot that as well. So just by pure intuition, we know we found to find I from V. So the relationship that governs it is I is equal to C dV by dt. Here C is 1. So I is simply dV by dt. So we just need to draw the derivative of this curve. So the derivative when the curve was 0 is 0. And the derivative when the curve was constant is 0 again, and it stays 0. It's obviously not 0 here because the derivative of this is not 0, and you can see that there is a change of 10 in a matter of 1 second. So the slope of this line is 10 actually, and slope is derivative. So we are going to get a current. I'm using this dash to line to show this abrupt change. So this is 10, the derivative is 10 because I is equal to 1 into dV by dt. 1 is the capacitance in this case, so I is equal to dV by dt. So V has a slope of 10 and derivative is a slope. So we are going to get a 10 ampere current during this time to charge a 1 farad capacitor in 1 second from 0 volts to 10 volts. So this is done purely intuitively. Right, so a simple problem can be done intuitively, but intuition does not help us when the problem gets complicated. So that's why we must know how to do a problem correctly, mathematically, without using intuition, and this is what learning is. So let us do the same problem purely mathematically. We are not going to use any of our intuition at all. So let us say we have this V. Can we write V mathematically? Vt as an expression, or maybe not an expression but a piecewise expression. We can see there are 3 segments of V: the V before 1, the V after 2, and the V between 1 and 2. The equation that governs this segment is different from the equation that governs this segment, is different from the equation that governs this segment. So we already are familiar with the mathematical way of writing this. So Vt is 0 when t is less than 1. It does not matter whether we use the equality sign or not, because the function is continuous and we can use, and we may not use, because when I am going to check questions, I am not going to check this small detail. Similarly, we know it is 10 when t is greater than 2 or greater than or equal to, and we know that the equation of the straight line here is going to be mx plus c, and the m we have just found is 10. So it is 10x, what is x here, t, and plus c. If we continue this line, it's going to pass from the cross the y-axis at minus 10. So the equation of this line is 10t minus 10 when t is between 1 and 2. So we can write it this way. So equality is covered for 2, equality is covered here, not here. For 1, the equality is covered there, not here. And you may not use the equality sign anywhere, or you may use for everyone. Every less than or greater than sign is perfectly fine with me. So this is a VT, a mathematical expression for VT, and now we need to find the derivative of this whole thing. So the derivative of 0 is 0. The derivative of 10t minus 10 is 10, sorry, plus 10. The derivative of 10 is 0 again. And we can obviously plot this thing to get the same plot for I. I hope you understand this, but let me make a question number 2 here as well. And suppose now that this graph of I is given and we have to find V. We should be able to do this again intuitively. We can very easily do that, but we should be able to do this graphically, purely mathematically as well. So here now we know V is equal to, from here, V is equal to 1 over C. We have, by the way, I written mathematically as this. V is equal to, and don't forget this minus infinity, t I dt. We know this c is 1, so we are going to get, we are going to integrate from minus infinity to the value of t that we are interested in, I dt. And what is I? I is this whole thing. So now let us come up with this thing. So what is v is equal to? We have to do it piecewise. We cannot do it like in one step, like we took the derivative of this vt and we took the derivative separately of each of the voltage in each of the interval. But we cannot do this in this case. So we have to do this for different intervals. So this is the general expression, v is equal to the integral of I dt. But let us write each interval separately. So for the interval, the first interval, for the interval when t is less than 1, so the value of t, if you put in the final result, the values of t should not be greater than 1. So for the first interval, when I is 0, v is equal to integral from minus infinity to t of 0 is going to be 0. So how we are going to plot this v? We are going to plot the v equal to 0 up till t is 1. We have this already here. So for the next interval, for t between 1 and 2, what is I? I is equal to plus 10 ampere. I'm ignoring the units for now. So what do we get? V is equal to the integral. Remember, always write everything if you are not comfortable with skipping steps. So what do we get here? 10 dt, and we are going to get, but this is very important now. We actually cannot write this from minus infinity to 10 because 10 is not from minus infinity to t. So 10 is not from minus infinity to t. So that's actually not correct. So this is very important thing. What was V we are trying to find V. What was V before t became equal to 1 is 0. So this V is actually, this should be looking at this expression of V that we came up with earlier on, that V is equal to V t naught, the starting time, plus 1 over C t naught to t of I dt. So what do we get here? So it is wrong to write this. So what should we do? It's not this. It is 1. 1 to t is 10. This is right now. So actually we could split this minus infinity to t thing into 1 to t plus, you already know integration by parts, minus infinity to t, and it's not 10 here, it's 0 dt. And we have already solved this thing. So we don't write it in this way. So what we do instead, we don't write, we write this as v at this thing 1. So from the previous interval, we should do this thing, this one bit as well. So find what is V at the last value of time. So what is V1? So V is 0 for every time up till and including 1. So V1 is 0. So this thing is 0. So what do we get here? An integral from 1 to t 10 dt plus 0. So what do we get here? We get 10 outside and we have 1, which is t limits from t 1 to t, we get this thing. And once again, for every interval we should find the last, what should be the value of v at the end of the interval. So what will v2? So v is 10t minus 10 or 10t minus 1. So we are going to get 10 into 2 minus 1. I'm going to get 10. So V2 is 10 volts. So here we have a straight line, 10t minus 10. So after this one, we are going to plot this line, and we know it starts from the same value where it left in the last interval. So it starts from 0 and goes up to 10, and it's a straight line. We can just plot it straightly. And for the last interval again, for the interval t greater than 2, v is going to be v minus infinity to 2. Now I'm bringing this earlier on, I dt plus 2 to t. And what is this? What is I after 2? I after 2 is 0. So this is this. And what is this thing? This thing is v at 2, which can be found from the previous case. Plus what is this thing? 0. So we get 10. So we see v stays at 10 after 2. So this is what we get here. So both of these we have extensively done this when we studied the relation between I and Q, charge and current. This is a similar relationship. You should be able to do this. However, I have done this very in a very detailed fashion, very with very minute detail, very meticulously, and I hope you follow this. You should be able to do this on your own for different types of graphs or expressions for V's and I's. So do it both way. Given a V, find I. Given an I, find V for a particular capacitor. You can find different problems in the book as well as the examples. The examples should be the first to be done, and then solve the unknown problems. And you can share the problems with each other on the group. That is what the Google Classroom is for.